The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone, and thank you for joining us on our call today. My name is Nicole Van Wert-Quincy from Transcat, and I'll be your moderator this afternoon. Our webinar topic is choosing the right calibrator. The topic is being presented by Steve Sabin from Druck BHGE, a GE company. Steve is the North American Senior Product Specialist for the Druck Pressure Measurement Product Group, part of Baker Hughes, a GE company. Starting his career as a sales engineer for a measurement and instrumentation manufacturer's rep firm in '91, Steve subsequently joined Druck in 1996 as a regional sales manager. Since then, Steve has held a number of sales, management, and commercial roles for Druck, and subsequently GE and BHGE, most notably Global Product Manager for Industrial Sensors. As part of his current role, Steve has a keen interest and focus on improving training efforts and materials for both internal Druck personnel as well as external customers. He has a degree in mechanical engineering from the University of Colorado Boulder and business management from Maryville University. We expect the presentation today to last roughly 30 to 45 minutes, and then we're going to open it up for question and answers. During any time of the presentation, you can send questions through the question box, which is in the right side in your webinar controls. I also want to mention that the webinar is being recorded. You will each receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. And at this time, I'm going to turn the presentation over to Steve. Steve? Steve, I can't hear you. Steve, there you go. Steve?
Yes, I'm here.
Okay, take it over.
Okay. Did you do the introduction already? Because I missed it.
I did. Was it not?
Okay. Yeah, I wasn't hearing it, but that's fine.
Okay. All right.
Thank you for the introduction, Nicole, and thank you for the opportunity to speak with everybody today. We are going to talk about how to choose the right portable process calibrator. Okay, just want to talk to the agenda of what we're going to try and cover in our discussion today. First, I'd like to scope a little bit, talk about what we are going to talk about, and maybe talk a little bit about what's outside of scope. The topic of calibration is wide and broad and deep, and we could spend a lot of time talking about it, but we only have 1 hour, so need to scope it down a little bit. Then defining goal or primary objective of calibration, so understand why we're doing the calibration, and then defining the approach to achieving that goal. Then equipment selection criteria to support the approach and philosophy of that approach to support that goal. And then at the end, wrap it up with some conclusions and possible recommendations. So scope of discussion. As the title of the talk describes, we're going to talk about the right way to, or how best to choose the right portable process calibrator. So outside of the scope of discussion is the laboratory calibration. I have a picture there of one of the fine technicians of the Transcat laboratory hard at work. We're not going to talk about the laboratory or benchtop calibration. Our talk is going to focus on field calibration, where we're actually taking calibrators, devices, instrumentation out into the field and doing calibration on site or in situ. Just wanted to make a brief comment on calibration and calibrators. So when we talk about calibrate, what does calibrate mean? My definition there is to standardize by determining the deviation from a standard so as to ascertain the proper correction factor. And obviously, calibration is the act or process of calibrating, or the state of being calibrated. And then a calibrator is a device used in calibrating something. Interestingly, when I was looking up these definitions, calibrator doesn't seem to be in the normal dictionary resources as a word per se. Obviously, I think the definition is understood. An additional comment on calibrator is the term calibrator can sometimes be viewed as a misnomer, as it does not always have, calibrators do not always have the capability to adjust output values of a device under test or a unit under test. But for the purposes of this discussion, the term will be used as a device that facilitates calibrations. So we'll talk a little bit more about that, which devices do and which devices do not do the actual adjustment. So defining goal and primary objective. Calibrations can potentially be required for a number of different purposes or for multiple purposes. One of those could be process performance or optimization, using instrumentation to improve the quality of our products. Safety concerns are always high priorities for organizations and certainly workers within those organizations. Quality assurance, compliance, meeting possible government regulations, industry regulations, corporate policy, or other compliant-driven requirements. Maintenance or preventative maintenance. And finally, functional testing. So functional testing isn't necessarily calibration per se, but we would be using the same or similar equipment to validate functioning equipment. So let's define the approach in achieving that goal. So defining the approach to achieving the goal. So the purposes that we have for performing the calibrations will drive the requirements and subsequently the required attributes of the calibration equipment that we will be using. Calibrator attributes and other considerations can include, but are not limited to, the parameters that we need to measure and calibrate, the performance of those devices for those parameters, the documentation required in keeping records of calibrations. We'll talk a little bit about utilization, how best to deploy calibrators and instruments in the approach to achieving our calibration goals. The ease of use and the implementation, an obvious consideration when we're buying new equipment. How easy is it going to be to use and to implement into current practices or new requirements? And at the end, we'll talk about, on this particular subject of approach, the price versus cost and considerations in that regard. So let's talk about parameters. They can be wide and varied, obviously, in any facility, process, petrochemical plant, power utility, other industrial facility. But the most common parameters covered by portable process calibrators are electrical parameters, voltage, current, resistance, obviously, temperature, so thermocouple devices, RTDs, pressure, and frequency pulse counting. So most portable process calibrator manufacturers cover most of these parameters. There are differences in the ranges, the types, and uncertainties specified, as well as features and functionalities of different calibrators. Other parameters, apart from these primary ones, may require other specific devices. In addition to those parameters, I wanted to mention briefly that oftentimes there are smart transmitter devices. Smart transmitters being devices that speak or can communicate via a digital protocol. And many portable process calibrators today have communicators built into the device, either as a standard or as an option. Communicators enable a lot of different functionality. They can provide the capability of a complete calibration, in effect, the ability to adjust the device into tolerance where it may be out of tolerance. Other smart features include the ability to rearrange or rescale a device, suppression by offsetting 0, other diagnostics, and other functionality via the digital communication. These other features, apart from just the facilitating the calibration, are typically only available if the calibrator or the communicator, is a fully functioning communicator. Some communicators have the ability just to facilitate calibration. Others are fully functioning, which means it has the ability to access all of the information and capability of a smart device. Most common digital protocols, communication protocols of smart devices are HART, the Highway Addressable Remote Terminal Communication, Field Bus, and Profibus. An additional comment on communicators: they require device drivers to communicate with your device. So be sure to check that the communicators under consideration have the necessary device drivers for your devices. There are libraries and capabilities within the communicator to store additional device drivers, but if a device driver isn't present, you may be able to communicate with the device in a generic mode, but all of the features and functionalities may not be available to you through the communicator. Performance, obviously another very important consideration when evaluating and selecting a process calibrator. We need to make sure that the calibrator is of a suitable level of performance to provide a necessary level of confidence that it is appropriate for calibrating the devices in the field. So measurement devices, we're talking about transmitters and transducers, gauges, switches, be they pressure, temperature, or electrical, are normally or usually specified differently than calibration devices. Measurement devices are typically specified by what we'll term accuracy, and I'll go into a little bit of the definition of what manufacturers typically define as accuracy. And calibration devices are typically specified by uncertainty. And again, I'll go into a little more detail on the definition of uncertainty, or what manufacturers are saying when they give a specification as an uncertainty. The fact that the devices and calibrators are specified differently can make evaluating the performance a little bit of a challenge. And so sometimes we're comparing apples and oranges in terms of performance definitions. So in order to properly define performance, it's important that we define the terms used to express it. So we'll talk about, as I said before, accuracy, and also want to make a comment about precision and what that means and how it differs from accuracy. And the components oftentimes discussed in the definition of accuracy of nonlinearity, hysteresis, and repeatability. Then talk about uncertainty, different kinds or levels of, if you will, uncertainty and standard, combined and expanded. Quick word about resolution and traceability. So accuracy is actually the closeness of agreement between a measured quantity value and a true quantity value of a measurand. So if we look at our graphic, our illustration there, we have the average or mean or median of a number of different values that will fall within a bell-shaped curve distribution, standard distribution. And the mean or median of that average when compared to the reference value, the calibrator or the standard, is commonly called the accuracy. Note that the precision is the closeness of agreement between indications or measured quantity values obtained by replicate measurements on the same or similar objects under specified conditions. So that's kind of the spread or distribution of those measurements when compared to each other. Common analogy used is a target where if the shots or the grouping is close to the center point, that's an accurate grouping. If they're close to each other, that's a precise grouping. If they're both close to the center target bullseye and they're close together, that's both a accurate and precise grouping. So precision is a little different than accuracy, and sometimes used synonymously, but it's important to define and understand the differences between the two terms. Accuracy for measurement devices is often expressed as the combined effects of nonlinearity, hysteresis, and repeatability, and is expressed as a given percentage of span or full scale. Sometimes also as a percent of reading, although you don't see that as commonly for devices. Percent of reading is a more accurate or more stringent definition, and more often associated with calibrators or standards. I've included an excerpt from one of our unique 5000 industrial pressure sensor platform data sheet and how we define accuracy on our data sheet. So for our voltage, current, and millivolt output pressure sensor devices, we state that the combined effects of nonlinearity, hysteresis, and repeatability are, for example, for the industrial grade, plus or minus 0.2% of full scale, and BSL refers to a best fit straight line, which is a definition of the comparison of those points together. I'll go into a little more detail on the definition of nonlinearity, hysteresis, and repeatability on the next slide here. So nonlinearity, so every device has an output and there is no perfect device. So it's rare, never, the case where the output of a device is perfectly linear, exactly what you would expect as an output for a given input. So we have to define the nonlinearity or the level of nonlinearity. So define typically using the best fit straight line as I referred to before, and that's the straight line that is fit using a least squares method through all of the calibration points that minimizes the maximum deviation from the line. That's the way we define it. Hysteresis is the difference in a given output for a given input when the variable is applied in an increasing and decreasing direction. So as we, for example, pressure, if we applied pressure to a gauge or a pressure sensor, and then we release that pressure, there may be some difference in the measurement at a given pressure point. And we define that as the hysteresis of the device. And then repeatability, similar to hysteresis, is defined as the difference in output for a given input when repeated applications under the same conditions are made. So again, using our pressure sensor example or pressure gauge, if we apply to pressure, release that pressure, apply to pressure again under the same conditions, the difference in output would be the repeatability or non-repeatability of that particular device. So we take these three components and we root sum square the contributing factors, and this is defined as the accuracy of the device. So a couple notes on this. There is no required standard definition for the accuracy statement of measurement devices, so there can be differences from one manufacturer to the next. These definitions and examples that I've provided here are typical. So it's important to look at, understand the definitions of accuracy or performance for the device being calibrated. So accuracy, as we've defined it here, does not account for other potential error sources, such as thermal effects, which are changes due to changing temperatures, or long-term stability, that's changes in output or changes in performance over time. There are other potential error sources that could contribute to the uncertainty of the device, and I'll move on to the definition of uncertainty on the next slide. A non-negative parameter characterizing the dispersion of the quantity values being attributed to a measurand. So what does this mean essentially? So again, looking at our graphic, whereas before we had a measured value compared to a true value, which would be the value that we would be using from our calibrator or our standard. And that difference for any given particular measurement is defined as the error. But there's uncertainty about both the calibrator being used, or potential uncertainty about the calibrator being used and the measurement being made. So the uncertainty of that range is the measured value plus or minus that uncertainty. So if I have any metrologists on the line, I want to apologize in advance for potentially oversimplifying this topic. It is, as I say in my note below, a broad and sometimes complex subject, and in-depth and detailed discussion is probably outside the scope of our conversation today, but if anybody's interested or wants to understand more, there are numerous resources available, probably the most complete of which is the BIPMs, the International Bureau of Weights and Measurements, the GUM, it's just is the evaluation of measurement data. It's the guide to the expression of uncertainty in measurement. It's available on the BIPM website, and you can take that up at your leisure for your reading for a more detailed explanation and a more advanced understanding. But for the purposes of our conversation, I just want to make the distinction between how calibrator performance is defined versus device measurement performance is defined. There can be multiple sources of uncertainty for a particular measurement. There's uncertainty associated with the test equipment being used. There can be uncertainty associated with the test equipment that test equipment is being calibrated against. The actual unit under test has uncertainty associated with it. There are uncertainty contributions from environmental variations, temperature and humidity, air density, buoyancy, gravity, altitude, others. There can be uncertainties that are from the methodology or procedures being used. It can be down to the person performing the calibration. And there can be other potential contributions of uncertainty to the measurement. The combined uncertainty is derived from a statistical analysis of as many relevant factors as can be determined and quantified. I've heard conversation and discussion that if you can characterize and understand the top 3 contributors, that you're probably grabbing the largest portion of the total. But again, that is a decision and a judgment that's down to individuals, groups. and companies that need to determine what's appropriate for their operation. So standard uncertainty, because we're using a statistical analysis, there will be a distribution of the uncertainties of the measurement. So a standard uncertainty basically is one standard deviation, which can capture, as the graphics shows, 68.2% of the potential deviations. The combined standard uncertainty is the statistical analysis of all of the different potential contributors of uncertainty. And then we talk about expanded uncertainty. So getting to the real point of the matter here, expanded uncertainty, sometimes called total uncertainty, is the product of the combined standard measurement uncertainty and a factor, K factor, larger than the number 1. So K is essentially equal to the number of standard deviations. So if we're using a multiplier factor, K factor of 2, then we would cover 95.46% of the potential deviation of the uncertainty. If we were using a K factor of 3, we would cover 99.73. So where does this come into play when we're actually looking at the specifications on a data sheet of a calibrator? I've included an excerpt from our DPI 620 Genie handheld multifunction process calibrator. And you can see that the specifications, there are several different columns. The one that I would point to is the total uncertainty column, which includes and is defined in a higher level of detail in our notes below where the specification is given. So our total uncertainty includes the temperature range over which it's defined. It includes the stability or instability over a 1-year period. It also includes the uncertainty associated with our reference standard that we're using to calibrate it, the nonlinearity, hysteresis, and repeatability, and as I said before, the typical long-term stability for 1 year with a K factor of 2. I wanted to make a quick comment about resolution because, again, I think probably most people understand this, but resolution is sometimes used synonymously or incorrectly with precision or accuracy. Resolution is the smallest change in a quantity being measured that causes a perceptible change in the corresponding indication. So whereas similarly we have the accuracy or true value and the measured value, and the difference between those two, the resolution is defined by the smallest increment that the device can measure. Traceability. Important to understand traceability, and what that term means. It's the property of a measurement result whereby the result can be related to a reference through a documented unbroken chain of calibrations, each contributing to the measurement uncertainty. So we're usually talking about, in this pyramid of traceability that goes up to the international system of units, we're down in the industrial measurements. So we're measurement devices in our transfer standards calibrators that we're using in the field are at the bottom typically of the hierarchy or pyramid of traceability. Now, those units and devices will be calibrated against other calibration devices that are transfer standards or higher accuracy standards. So secondary laboratory, primary laboratory, up to national metrology institutes. So it is possible to keep a documented unbroken chain of those calibrations by tracing that calibration. So the big question, that's a lot of information in a very short period of time, and is it all
Stephen, I can't hear you. We lost sound, Stephen. Okay, I'm going to give Stephen another minute or so. He must be having technical difficulty because his sound went completely out. So we'll give it, another 30 or 60 seconds, and if we don't hear him come back, I'll end the webinar and we'll send everything via follow-up. Sorry about that, everyone.
To the accuracy of the device under test provides a 4-to-1 ratio, there should be a very high level of confidence that the standard, the calibrator, is appropriate for use for that device. Sorry, Nicole, can you hear me?
I can hear you now, but you went out for a couple minutes and we didn't hear anything for like 2.
Did I really?
Yeah, but I can hear you now.
Okay. Sorry, I was. My sincere apologies. I had the dialog box on a different screen, and I was focused on the screen that I was with the slides.
All right, well, I'm glad you're back.
Should I? Yeah, glad I'm back too. Should I backtrack, or where did you?
Went to this slide, I lost you, or I think everyone did. So maybe just start from this, how to choose the right portable process calibrator slide, or go back like 2 minutes in the content.
Okay. Did you hear me on this slide?
Like right that, yeah, for some of it, and then we lost you.
Okay. So I'll if I pick up here, I probably catch what I missed.
Probably safe.
Okay. All right. So let me reset myself. So is all of this relevant or important? Well, it depends. So required performance can be defined a number of different ways. The total accuracy ratio would be the ratio of the calibrator to, or the device under test to the calibrator. So if the calibrator or standard being used is 4 times more accurate than the measurement device, then we're maintaining a 4-to-1 accuracy ratio. Similar to, but different, because we're talking about uncertainty, would be the total uncertainty ratio. And again, if the uncertainty of the calibrator was 4 times better than the uncertainty of the measurement device, if known, then that calibrator would be appropriate if we're using that criteria. Measurement uncertainty analysis and probability of false acceptance measurement uncertainty and probability of false acceptance are typically not required in field calibration. So we revert to generally accepted best practice of trying to maintain a accuracy ratio or uncertainty ratio, probably more commonly accuracy ratio, and of an accuracy ratio of 4-to-1, which is much more common. So just to note, and hopefully try to tie this all together, uncertainty is a much more stringent definition of performance than accuracy. It takes into account a lot of other factors besides, well, in addition to what's defined in accuracy, a lot of other potential error sources. So if we're comparing the uncertainty of a standard, a calibrator, to the accuracy of a device under test, and we still have a 4-to-1 ratio, 4-to-1 ratio of the accuracy of the device to the uncertainty of the calibrator, then there should be a very high level of confidence that the standard is appropriate for use calibrating our measurement device. So now we're going to move on to documentation. So we need to keep a record of all these calibrations that we're doing, and as honest and forthright as we all are, I'm sure that we can't just go out into the plant and do a calibration and go back in and tell the boss man that, hey, yeah, I checked it, it's good. We got to keep a record of it, right? So there's different levels of documentation that we can do or look at. The first one is the old reliable pen and paper with the calibrator. Stepping up from there, we can use an Excel spreadsheet or Access database plus the calibrator. Then we move into software where we have just a generic calibration software where we can effectively facilitate moving calibrations from the calibrator directly into a software program. Calibration management software plus a compatible documenting calibrator. So this is where we can actually define a process, procedure, routine, and the variables such as tolerance of devices, etc., and be able to download that procedure to a calibrator, perform the calibration, and then upload it back to the software, making it in effect a paperless calibration. And then one step above that is a maintenance managed system plus the calibration management software and a documenting calibrator, where this would provide the capability and features to be able to track and trend calibrations, do analytics, preventative maintenance, other capabilities beyond just keeping a record of the calibration being performed. So pen and paper, there are advantages and disadvantages of each one of these approaches. Obviously with pen and paper, it's inexpensive to set up. There's not a lot of setup. You don't need any IT resources. Users don't have to be computer literate, don't even need a laptop per se necessarily. Just writing down values off a calibrator onto a calibration sheet. Disadvantages would be reliance on calibration technicians. It's somewhat labor intensive or more labor intensive. There's a need to have a rigid or defined process to follow. Slightly more difficult to maintain and control. You have to archive paper, a lot of paper potentially, and it's impossible to analyze the data, or at least it's very difficult to. And there's a large possibility for defects, and by defects we mean transcription errors, writing down the wrong value or reading the wrong value off the instrument, or potentially being copied down when the data is moved to another format, i.e. into a spreadsheet. So while it's cheap and easy, it does lead to some potential issues with cost, effort, and accuracy or quality of data. An Excel spreadsheet or an Access database, obviously, again, it's inexpensive to set up. It's more legible and reduces or eliminates transcription errors or other errors associated with writing down values. And you do have it in a digital format on a computer, so it helps with the safekeeping of records and backup system and being relatively easy to retrieve. The disadvantages were, again, you need experienced calibration technicians. You have to have a fairly rigorous process to follow. Slightly more difficult to maintain and control. Need an Excel or Access expert, and not necessarily an expert, but somebody that's reasonably well versed in Excel or Access database management. to ensure its proper safekeeping and retrieval. There's additional steps to analyzing the data, and there's a possible need to integrate that database with other software if records are being kept in other areas or other departments.
Okay, Stephen's clearly having technical difficulties on his end this afternoon, and I apologize for that. We'll give it another 30 seconds or a minute and see if it clears itself up, and if not, then I'll bring the webinar to a conclusion. So just bear with me for a minute or so, folks. Thank you.
Of calibrators. Is there sufficient modularity to provide flexibility of ranges and accuracy to cover all the requirements? And how can calibrations be covered when equipment is out for recal? So we want to make sure we have the proper tools that do the proper job. We don't want our guys, our technicians and operators sitting on the I-beam there. We want them properly equipped with the tools, ready to go out and perform the jobs and functions that they need to do. So one of the major determinations in selecting a process calibrator is they come in two primary categories. One's a single function calibrator that'll do one or I guess a couple of things, versus a multifunction calibrator where you have one calibrator that can do all of the parameters that we discussed before: electrical, temperature, pressure, frequency, pulse count, etc. So each approach has, again, its advantages and disadvantages. If you have single function ones, you can deploy those for specific calibrations. For example, if you have a lot of RTDs that need to be done, you can deploy just the RTD and loop calibrator, or thermocouples, or any one of the individual ones, while another technician or operator could be using one of the other instruments. The downside is if one operator is doing multiple calibrations on different parameters, they have to carry a bunch of stuff. So it's always looking for the balance, weighing the pros and cons of having a number of calibrators that do a number of different things, or one calibrator that does everything. So ease of use and ease of implementation. Does a calibrator cover all the parameters needed? Is a calibrator intuitive to use, or does it require extensive training? And if it does require extensive training, does the vendor provide that? Is it free? Is it for a charge? Is it similar to other calibrators currently in use, or is it a dramatic change? Will it fit into current practices, capabilities, or is there a change required? Is it compatible with software in place, for example? I guess fortunately for vendors, or fortunately for customers, with developments of digital display technology, many calibrators are relatively easy and intuitive to use, as well as having on-screen graphics and icons that make functionality simple to use and understand. So a lot of the ease of use and implementation questions as far as the operation of the calibrators themselves are reduced, if not entirely eliminated. Price and cost. So in the end, it always comes down to price versus cost. So when I talk about cost, I'm talking about value, which equals essentially quality. So considering economic costs are oftentimes defined as the accounting cost, which is the actual dollars paid for something, plus the opportunity cost, the risk of the gain versus the loss. So calibration equipment can be expensive and oftentimes within many organizations viewed purely as an accounting cost, which is essentially a non-returning investment. But there's always an opportunity cost associated with properly performing or not performing calibrations that should be appropriately balanced to potential return. So it's not always the best thing to choose the cheapest, and it's not always necessary to choose the most expensive. Again, finding the balance. So coming down to conclusions and recommendations and trying to tie this all together. It's important to, and I think possibly obvious, but always good to state in a logical and constructed manner, the steps to making the right choices. First, we have to understand the organizational calibration goals and objectives. Then we can develop an approach to addressing those goals and objectives. And then we define the selection criteria for equipment, calibrators, to support our approach. Always important to review multiple offerings by engaging different vendors, evaluating top contenders. Most vendors, at least the ones I'm familiar with, are very open and willing and enthusiastic about providing demonstrations and evaluations, finalizing decisions. But then I'd also suggest or possibly recommend that it's important to stay engaged with the vendor for aftermarket support. Our good friends at Transcat can help you with all of these steps in your defining and selection process. Possible consideration as a suggestion, a recommendation, defining a selection matrix, helping tie together the goals and primary objectives to the approach or criteria for selection. So, for example, if we're looking at process performance improvement or optimization, obviously the performance of the calibration equipment is going to be very high, right? If we're looking at the maintenance or functional test capability, where we're just trying to determine if something's working or not working, performance may not be as much of an issue. Other parameters or other aspects are going to depend on the organizational goal again. So compliance, it may be that a calibration needs to be done, but it may not be a overly rigorous or tightly defined tolerance requirement that needs to be met. So it could be high or it could not be high. So working through a selection matrix like this can help define the priorities and then help narrow down selections. Unfortunately, there is no perfect portable process calibrator that will cover every parameter exactly the way every technician wants it to. But fortunately, there are many, many calibrators on the market, and through careful consideration and review, an optimal solution can be found. So that concludes the information that I had to present today. I think that, Nicole, if I could hand it back to you for covering the the next two slides on the current promotion and your contact information.
Thank you. Yep, I wanted to make everyone aware, and we'll send this in the follow-up email as well, that we are promoting. There is an ongoing promotion that ends at the end of October, where you can save up to 25% on the Druck BHGE, the DPI 620 Gen 2 multifunction calibrator. That's with the trade-in. We have the full details at our website at transcat.com/deals, or you can feel free to call and speak to any of our sales reps. We'll be able to help you walk through that. Our contact information is here, our 800 number. You can email me directly, and you'll have that information as well within the invite. So I'm going to move on to the question and answer portion of the webinar. And as a reminder, if you have questions to ask, you can submit them within the webinar controls. There's a question section, and you can type the questions in and submit them. Steve, we had a couple questions basically around calibration cycle. So in other words, if the manufacturer doesn't specify the recommended frequency for calibration, what is the best basis to determine what's acceptable?
Great question. So it's oftentimes there is a requirement, a customer requirement, corporate organizational requirement for the calibration interval. If the calibration stability component is not specified in the calibrator definitions, I think most that I'm familiar with or aware of define some time interval over which the specifications are valid. But if it's not, the recommendation would be to define some interval, perhaps 3 months, perhaps 6 months, track that calibration to find, if you do repeated calibrations and find that you're within tolerance on your standard or calibrator on a 3-month interval, then extend it to 6. If you're within tolerance on a 6-month calibration, then extend it to 9 or 12. Again, I would say that I think most manufacturers do include the stability component in their performance specifications. But if not, that would be my recommendation as to how to handle that. If there's not some other organizational compliance or other definition of the frequency of calibration requirement.
Okay. When discussing calibrators, you mentioned that some calibrators are not actually capable of making adjustments to devices. Are there calibrators that do have the capability to perform adjustments to the device?
Yes, there are, and I think oftentimes, so on an analog device where you're looking at a current or voltage or other analog output, it's more difficult for a calibrator to make the adjustment on that device. When you get into digital devices, like where we talked about the smart devices, that the calibrator can have the capability to reset the 0 and or span trim to bring it within tolerance through the digital communication capability. This is the capability of our Druck DPI 620 Genie. It's a function of most digital communicators that provides that capability of making the adjustment.
Okay. Is there any way to keep a digital record of a calibration without having to purchase or integrate software?
Yes. So there are calibrators. Our 600 series has the capability where you can actually define or store data onto the calibration unit itself. So you can set up a data storage file, store the calibration information to that file, and then be able to upload that stored file to a laptop or PC, usually in a CSV file format. Doesn't require any special software, but it does facilitate getting the calibration information out of the device into a digital format on a laptop or PC, and then that data can be exported or pulled into an Excel spreadsheet or other database format.
Okay.
So the benefit of that is not having to make a software investment.
All right. Is there any way to fully automate a field calibration?
Yes, it sometimes depends on the parameter, but with calibration software, where you can actually define the procedure and all of the requirements within that procedure, such as the tolerances of the devices, it's possible to connect to a device under test, start the procedure, and the calibrator will step through all of the calibration points of the routine and save those points, and then that stored calibration, once complete, can be uploaded back to the software program. So apart from making the connections and essentially pressing the start button and monitoring the tolerance, the operator would not need to do anything additional other than accepting the intolerance calibration points.
Okay, that concludes our time for today. Thank you so much, Stephen. For anyone on the line, if you have further questions or you'd like to find out more about what Transcat offers as far as new instruments, we offer new instruments, used instruments, rental, and calibration services. You can contact us at 800-828-1470 on the web at transcat.com. You can email me directly as well. Thank you all for joining us today. Sorry about the technical difficulties. We will send out a copy of the recording, and we hope you got something out of the presentation today. Thanks so much.